Hey guys, it's Mr. Lowry. This is basically what we covered in class on 1123, which is a Monday if you're in cohort A, and this is the lesson for 1124 if you're in cohort B. It corresponds with sections 3.1 and 3.2 in your geometry book. So if you want to, you can kind of peruse through your geometry book for this section, 3.1, parallel lines and transversals. And this starts on page 126. It's got some good definitions in here for you, like this one of a transversal we're going to talk about, and it has names of different kinds of angles which we're going to talk about. So this is on page 128. This is a pretty good diagram, key concept that you can write down in your notes or something that you might want to remember. And then in 3.2, this section, angles and parallel lines, this starts on this is 3.2 and it starts on page 133. It has just some postulates that we're going to talk about in theorems. So there's this postulate right here, and there's some theorems here. We're going to go through a few of these theorems together in just a second. So I'm going to try to get you all that information, or a lot of that information, just kind of in note form here, and you can obviously go back and look through those sections. I just wanted to give you kind of another reference for that. What we're talking about today is parallel line angles, names, and angle theorems. So what we have here is we have this shape where these two lines, L and M, are crossed by another line. So typically when we name lines, we use lowercase, scripty, or cursive kind of letters. So here's L for line. Typically after L you use M and then M, just because that's the next letter in the alphabet. In this case, I called this line T, and I picked that letter because this line is called a transversal. Okay, it means it crosses over some other lines. So when we do that, we get all these angles. We have, basically 8 angles here, and we want to talk about different names for the relationships that we see here. Okay, the first kind of definition for today is what corresponding angles are. I'm going to talk through that, and then I'll list for you the corresponding angles here. So corresponding angles are essentially angles that are on different intersection points, but they are in the same position. Okay, so if you look at these two intersections here, we have L, and that's crossed by T, and then we have M, and that's crossed by T. So if you look at this intersection between L and T, there are 4 angles here, 1, 2, 3, and 4. I got a top left, a top right, a bottom left, and a bottom right. I also have 4 angles from this intersection with M and T. So again, top left, top right, bottom left, bottom right. So corresponding angles are in the same position in different intersections. So if you look at this one, angle 1, for example, that's in the top left corner. This, number 5, is also in the top left corner of this intersection. So angle 1 and angle 5 are in different intersections, but they're in the same position, the top left position. So what I would say here is angle 1 and angle 5, I'm listing those as a pair of corresponding angles. And there's a few other pairs here. So 1 corresponds to 5. Okay, angle 2 and angle 6 correspond to each other because they're both in the top right corner. So 2 is the top right of this intersection, and 6 is the top right of this intersection. So I would say that angle 2 and angle 6 are corresponding angles. Okay, bottom left we have 3 for the top intersection. For the bottom intersection, the bottom left corner is 7. So we got 3 and 7. So we know that, let's do it down here, angle 3 and angle 7 are corresponding angles. Okay, and then we also have angle 4 and angle 8, the bottom right. So the bottom right of this intersection is angle 4. The bottom right of this intersection is angle 8. Okay, so those are all my corresponding angles. So again, same position in a different intersection. Okay, alternate interior. Let's talk a little bit about what interior means first. So interior means in between these two lines. Now, these two lines look parallel, and I've drawn them to be parallel. You don't have to necessarily have parallel lines to have alternate interior angles. We're going to talk about when that is the case in this lesson today. But the interior angles are basically the ones that are in between the pair of lines that are kind of going in the same direction. or if these are parallel, the ones that are in between the parallel lines. Okay, so this is the interior. 3, 4, 5, and 6 are all interior angles because they're between L and M. Over here, above L and below M is our exterior section. Exterior just means outside, interior means inside. So here's the 4 inside angles, and here's the 4 outside angles. Okay, alternate means opposite in this context. Okay, so we're looking for angles that are opposite and they're in between L and M. So alternate means they're on opposite sides of the transversal, and they're also on opposite lines, the lines that are like different. So angle 3 is on the inside, and it's opposite, or is over here on the other side of the transversal on the other line M. So it's like across from it, across the transversal. So this is angle 3 and angle 6 are alternate interior angles. Okay, see if you can pick out the other pair of alternate interior angles. They're inside, in between L and M, and they're on opposite sides of the transversal. One's on L and one's on M. If you chose angle 4 and angle 5, you are correct. Those are also alternate interior angles. Okay, so those are our 2 pairs of alternate interior. 3 and 6 are alternate interior, 4 and 5 are alternate interior. Okay, let's take a look at our alternate exterior. So again, alternate in this case means opposite. They're on different lines, they're across from each other on opposite sides of the transversal, but this time they're exterior. So here's 4 exterior angles. Okay, we want 1 and 8. Those are alternate exterior. They're exterior angles, they're on opposite sides of the transversal. One's up here above L, and the other one's here below M. So angle 1 and angle 8 are alternate exterior. Okay? See if you can figure out what the other pair is. If you said angle 2 and angle 7, you are correct. So 2 and 7 are alternate exterior angles. Okay? And then the last one here is consecutive interior angles. Okay, consecutive in this context means they're on the same side, and then interior means they're in the interior. So alternate means kind of like opposite side, consecutive means same side. So we're talking about their interior angles, right? These are our 4 interior angles, but they're on the same side of the transversal. So 4 and 6, angle 4 and angle 6 are a pair of consecutive interior angles. Okay, so you try to find the other pair. If you said angle 3 and angle 5, you are correct. Those are consecutive interior angles. Okay, so those are just names. Those are just labels that about these relationships. If you have this kind of a situation set up and you want to talk about 1 and 8, you call them alternate exterior. If you want to talk about angle 4 and 5, you call them alternate interior, and so on. Now, what I want you to notice here as you look at this figure, there's other angle relationships in here as well. So like vertical angles, for example. 1 and 4 are vertical angles. 2 and 3 are vertical angles. 5 and 8 are vertical angles. 7 and 6 are vertical angles. We also have tons of linear pairs, like 1 and 2 form a linear pair, and 2 and 4 form a linear pair, and 1 and 3 form a linear pair, and 3 and 4 form a linear pair. And same with 5 and 6, and 6 and 8, and 7 and 8, and 5 and 7. So there's tons of vertical angles or tons of linear pairs. Those are going to be really helpful when we start proving some theorems here. Okay. Here's some things that we want to prove. Now that we got the naming scheme kind of down, there's a few theorems, postulates that we need to talk about. Okay. This all comes back to parallel. If the 2 lines that we were talking about are parallel, L and M, then we get 4 results. We get the consecutive interior angles supplementary, we get the alternate interior angles congruent, the alternate exterior angles are congruent, and the corresponding angles are congruent. So that's 3 congruents and 1 supplementary. Okay, so going back to this figure, if we know for sure that these guys are parallel, L and M are parallel, then we know that the opposite interior are congruent, so 4 congruent to 5. We know 3 is congruent to 6. We'd also know that the corresponding angles are congruent. So 1 congruent to 5, 2 congruent to 6, 3 congruent to 7, 4 congruent to 8. We knew that the alternate exterior angles are congruent. So 1 is congruent to 8, 2 is congruent to 7. And we also know that the consecutive interior angles are supplementary. So 4 plus 6 equals 180, 3 plus 5 equals 180. Okay, so those are things that you may already know and that you may already talked about in a previous class, but our goal today is to prove these. We're going to try to reason through and show that these are actually the case. Okay, so let's start with this one here. I put them in this order for a reason. Let's talk about consecutive interior angles. So we're saying if two lines are parallel and they're cut by a transversal, then these two angles have to add up to 180. If you think about that for just a second, you might recognize that kind of idea, and essentially that's kind of going back to Euclid's fifth postulate. So this is a handout that I gave you not too long ago. It has Euclid's 5 postulates. We talked about Euclid's elements and an axiomatic system. And this is Euclid's fifth right here. The language is kind of hard, so we talked about this last time. Let me break this down for you a little bit and see if we can kind of understand what this is saying. If two lines are drawn with intersect a third, okay, so two lines are drawn and intersect a third. Well, that's our lines on our transversal, right? This is our L and our M and our T, basically. Same kind of a situation. And they're drawn in such a way that the sum of the interior angles, so these two angles, let's call them 1 and 2, is less than 2 right angles. So if we basically draw them in a way where the measure of angle 1 plus the measure of angle 2 is not equal to 180. Now, it says less than, but if they're less on this side, they're greater on this side. And if they're greater on this side, then they're less on this side. So either way, if these don't add up to 180, then the other ones don't add up to 180 either. So let's say measure of angle 1 and measure of angle 2 is not equal to 180. If that's the case, then the two lines inevitably must intersect each other if extended far enough. So if these two don't add up to 180, then these have to cross. Okay? Now you might be familiar with, let me finish this out, intersect, L and M intersect. You might be familiar with an idea called the contrapositive, which is a statement that is logically equivalent to a statement, but you get there by like switching the order of the statements and negating them. So another way of saying this, Euclid's fifth postulate, is basically to say if these two guys are parallel, meaning they don't intersect, if they don't intersect, then these do have to equal 180. So if these two lines, L and M, are parallel, then measure of angle 1 plus measure of angle 2 equals 180. Now essentially, that is exactly what we're talking about with corresponding angles, right? Not corresponding, consecutive interior, excuse me. Euclid didn't use this language, but he said basically these two consecutive interior angles are supplementary if these guys are parallel. That's another way of kind of interpreting this Euclid's fifth postulate. Okay, so that's kind of where we're going. Let's go back to our little note sheet here. Okay, and let's talk about how we know this is true. Okay, consecutive interior angles are supplementary. If L is parallel to M, then consecutive interior angles are supplementary. So again, if these two are parallel, then this measure of angle 4 plus measure of angle 6 equals 180, or measure of angle 3 plus measure of 5 equals 180. Essentially, that whole idea is just Euclid's fifth postulate with different language. Okay, so this guy right here, our justification, we're not even going to really do a proof. We're just going to say that's Euclid's fifth postulate. It just has some different language in it, but that's essentially what we got there. Okay, so we've kind of established that that's the case already based on something that Euclid said. Okay, now what we're going to do from here is we're going to try to prove these guys. We're going to try to prove that alternate interior angles are congruent, alternate exterior angles are congruent, and the corresponding angles are congruent. Okay, let's start with alternate interior angles. Now, when we prove this one, this is going to be a little bit of work at first, but the proofs after get so much easier. They kind of like fall like dominoes. Once you get one, the other ones are super easy. All right, so let's start with the alternate interior angles theorem. I'm going to use a little bit of abbreviation here. I'm going to say alt int angles theorem. Okay, it's just kind of shorthand there. If L is parallel to M, then, okay, now what we want to do is we want to set up a situation. Let's go back and actually kind of read the language here. So if we have two parallel lines cut by a transversal, we want to show that the alternate interior angles are equal to each other, or congruent. Okay, so what we're going to do is we're going to set up a figure, and we're going to label it in such a way that we can assume the if part, and then we're going to prove the then part. So I'm going to do a couple parallel lines here, and we're going to add our transversal. Okay, and the alternate interior angles theorem says if you have two parallel lines cut by a transversal, then the alternate interior angles are congruent. So I'm going to make these parallel using my little symbol for parallel there on the figure, and I'm going to just write in some angles here. I'm going to call this one angle 1, and this one angle 2, and this one angle 3. So the given here is that the lines are parallel. So here's my statements, here's my reasons. Okay, what we can assume is that L is parallel to M. And the reason for that is given. Remember, when we're trying to prove a theorem, we use the if part as the given and then try to prove the then part. The if part is if two lines are parallel and cut by a transversal. The then part is alternate interior angles are congruent. So what we're going to try to prove is that angle 1 is congruent to angle 3 because those are the alternate interior angles in my figure. And if we can do that, then we're good. We've showed alternate interior angles are congruent for parallel lines. All right, so here's our given. Okay, now we also might want to mention that angle 1 and angle 3 are alternate interior angles. Okay, so step 1, step 2. Now we can kind of tell that from the figure. That's just a definition. We talked about the definition of alternate interior angles. So I'm going to go def of alt int angles. So abbreviations are fine, encouraged maybe even. Just make sure that you're clear and you're not abbreviating to the point where people can't understand you. Okay, cool. So let's talk about the parallel for a second. Where does the parallel get us? How does parallel help us? Well, we just talked about a minute ago that if these lines are parallel, then 1 and 2 have to add to 180. That's Euclid's fifth postulate. So let's go ahead and list that. Don't know how we're going to use it yet, but let's go ahead and list it. The measure of angle 1 plus the measure of angle 2 equals 180. Okay, the justification for that, the reason that we can say that, is Euclid's fifth postulate. Okay, cool. Now, we want to talk about 1 and 3. We just talked about 1 and 2. Maybe if we talk about 2 and 3, then we can somehow relate 1 and 3. So 1 and 2 we know something about. What do we know about 2 and 3? Well, 2 and 3 are a linear pair. They're two angles that when you put them together form a straight line. And what we know about those is that they are supplementary. So let's say angle 2 and angle 3 are a linear pair. Okay, that's just the definition of a linear pair. It's two angles whose non-common side form opposite rays. So here's your opposite rays, basically that straight line right there. Okay, so angle 2 and angle 3 are a linear pair. I'm going to say def of linear pair. Okay, step 5. Well, we proved last week that linear pairs are supplementary. So I can say the measure of angle 1 plus the, measure of angle 2, plus measure of angle 3 equals 180. Okay, that's the supplement theorem that we proved last week. Okay. Step 6. Okay, now if measure of angle 1 plus measure of angle 2 equals 180, and the measure of angle 2 plus the measure of angle 3 equals 180, then I can set these two expressions equal to each other because they're both equal to 180. So I can say that the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 plus the measure of angle 4. Sorry, running out of room a little bit. But the measure of angle 1 plus the measure of angle 2, oh shoot, sorry, let me rewrite that. That's not exactly what I wanted. Excuse me. The measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. We don't have an angle 4 in here, right? You might be wondering where that angle 4 came from. Yeah, we don't have one. So 1 plus 2 is 180, but 2 plus 3 is 180, so 1 plus 2 has to equal 2 plus 3. That's what I have here. And that's a substitution. We're just replacing, the 180 with what 180 is equal to. So I'm going to say subst prop of equality. Okay, kind of do a shorthand there, but that's the idea. Okay, now what we can do now is, the goal is we want to get angle 1 and angle 3 congruent to each other. So their measures we want to have equal to each other. But we have this extra angle 2. But since this is an equation now, I can subtract the measure of angle 2 from both sides and keep this equation equal still. I can keep it balanced. So if I subtract the measure of angle 2 from here and the measure of angle 2 from here, my equation is still balanced, but I'm left with the measure of angle 1 equal to the measure of angle 3. And that is the subtraction prop of equality. Okay, so be careful with your abbreviations, subst and subter. If you use sub for both, it's hard to tell whether you're talking about substitution or subtraction. That's why I'd use subst and subter, so we can tell which is which. Okay, and then the last one is that angle 1 is congruent to angle 3 because congruence means equal measure. So if you show their measures are equal, then you can show that the angles are congruent. So that's the definition of congruent angles. And for short, I put def of cong. Right, cong stands for congruent. So definition of what congruence means. Congruence means equal measure. All right, so we started out with parallel lines. That's all we assumed, parallel lines. From there, we use Euclid's fifth to say 1 plus 2 equals 180. Then we use linear pairs to say that 2 plus 3 equals 180. We did some algebra stuff, some substitution and a subtraction, and we got 1 is congruent to 3. And that was our whole goal. So we started out trying to prove this theorem. We just did, and now we can use this. We just unlocked this theorem for our next proof. So we can assume that if two parallel lines are cut by a transversal, then the alternate interior angles are congruent. We can now use that fact. We've just proved it. Okay. The next two proofs are actually going to be much faster than this because now that we have this first guy, we can use it, and it gets a whole lot easier. Okay, let's take a look at the second thing we want to prove here. So back over here on this first note page, we wanted to prove consecutive interior angles are supplementary. We talked about that essentially that's Euclid's fifth postulate, and so we don't really have to prove it. It's already just stated in different language. We wanted to prove, alternate interior angles are congruent, which we just did. Check. So the next one we want to prove is that alternate exterior angles are congruent. Okay? So let's do that theorem next. I'll help you set it up and walk you through it, but I think you might be able to get there on your own once I set it up. So let's give it a try. Okay, the next one, I'm going to do alt ext angles theorem for short, right? Alternate exterior angles theorem. This theorem says that if two parallel lines are cut by a transversal, then the alternate exterior angles are congruent. So if two parallel lines are cut by a transversal, then alt ext angles, alternate exterior angles, are congruent. I'm using a little shorthand there with the congruent symbol and abbreviations. That's the idea. So we need to set up a situation where we have the given, the if part established, and then we try to prove the then part. We're going to assume parallel lines, and we're going to prove alternate exterior angles. So let's create a figure, let's label it, and then we'll use that figure to do our proof here. Okay, so there's our parallel lines. We'll do a little transversal here. Okay, now we're trying to prove that alternate exterior angles are congruent. So let's label some alternate exterior angles. Let's call this guy 1 and let's call this guy 4. Okay, then let's get some other angles here. Now we just proved something about alternate interior angles, so maybe let's put a pair of alternate interior angles in there to see if we can see if that helps. Okay, we'll call this guy L, we'll call this guy M, we'll call this guy T. So we got some angles labeled, we got some lines labeled. Okay, we're going to assume L is parallel to M, because again the if part is if two parallel lines are cut by a transversal, or here's two lines, here's a transversal. We're going to assume L and M are parallel. And we're going to prove 1 is congruent to 4. So our whole goal is to prove angle 1 congruent to angle 4. All right, here we go. So we got our columns, statements, reasons, and we're going to start out with step 1, L is parallel to M. And this is the kind of notation for showing that. That's given. Okay, we can see that 1 and 4 are alternate exterior angles, so again our goal is to prove that. Let's talk about what parallel gives us. Okay, well, parallel lines, L and M, we just proved a second ago that if these lines are parallel, then the alternate interior angles are congruent. Okay, so we can say that angle 2 is congruent to angle 3. And our justification is the alternate interior angles theorem that we just proved a second ago. Awesome. Okay, so that's cool. Let's talk about other angle relationships we have in here, because 1 is congruent to 2 because these are vertical angles. So we already proved the vertical angles theorem last week, and we know that vertical angles are congruent by that theorem. So I'm going to say that angle 1 is congruent to angle 2. And I'm going to say vert angles theorem. Okay, I'm also going to say, I'm going to talk about these vertical angles. So angle 3 is congruent to angle 4. And that's a vertical angles theorem as well. So if 1 is congruent to 2 and 2 is congruent to 3, then 1 is congruent to 3 because of the transitive property. And if 2 is congruent to 3 and 3 is congruent to 4, then that means that 1 has to be congruent to 4 by transitive property. So 1 is congruent to 2, 2 is congruent to 3, 3 is congruent to 4. Okay, well then all 4 of these guys are congruent. 1 has to be congruent to 4. So there's, you know, if you want to be really, really strict about it, you can be, and when you use transitive property, you kind of only want to do 3 at a time. But let's just kind of, that's the basic idea of it. Let's go ahead and kind of wrap it up, and we'll say that angle 1 is congruent to angle 4 by the transitive property of congruence. Okay, now we probably would want to do it in maybe a few more steps to be a little bit more detailed. Again, to say 1 is congruent to 2 and 2 is congruent to 3, therefore 1 is congruent to 3. And then we would say 3 is congruent to 4, and then say 1 is congruent to 3, and 3 is congruent to 4, so 1 is congruent to 4. Again, usually transitive property only does like 3 at a time instead of 4 at a time, but you can kind of see how that chain of reasoning is going to work out. So I think this kind of makes sense here for a proof and for reasoning to get you going with this theorem. Okay, so that's the proof of the alternate exterior angles theorem. So now on your homework, you can use that idea that if two lines are parallel and they're cut by this transversal, then the opposite exterior angles are congruent as well. Okay, the last one we're going to prove here is that the corresponding angles are congruent. Okay, that's the last relationship. And we can do something really, really similar here. Okay, so again, let's draw it out. Let's talk about our proof. Let's represent that proof with a diagram that we can label and then use those labels to help us finish the proof. So this is the consecutive, sorry, not I get those words mixed up sometimes. Corresponding is what we want. Corresponding angles theorem. Okay, this one's about corresponding angles, of course. So the theorem says if two parallel lines are cut by a transversal, then the corresponding angles are congruent. All right, so we got to start with parallel lines. The if part, again, is the part that we're going to assume. So we need parallel lines, we need a transversal. The then part is what we're trying to prove. So here's the given, okay, and then this stuff is what we want to prove. Assume the if, prove the then. So let's get some parallel lines up here. Let's get a transversal. Okay, L, M, T. You can label them differently, but that's okay. But those will work just fine too. So let's put some angles on here. Okay, we want some corresponding angles. So let's call this guy angle 1, and let's call this guy angle 3. You don't have to call them that, but you know, that's good enough. And let's use a little helper angle. Let's put one right there. That's angle 2. Okay. So we got these alternate interior angles. We got these vertical angles, right? And what we want to show, we want to prove the corresponding angles are congruent. So we want to prove angle 1 is congruent to angle 3. Okay. That's our goal. We start with the fact that L and M are parallel. This is essentially going to be the same proof that we just did. So if you can, I recommend that you try to do this proof on your own. See if you can follow the reasoning of the last one. And then if you get stuck, maybe come back to the video. So I would pause it here and try to complete this proof on your own. If you can't quite get there, that's okay, but you definitely want to be practicing proofs and reasoning and stuff. So you don't want to, you know, be completely reliant on the videos to help you. They're more to just get you started, I guess. So we're going to start with L is parallel to M. Okay, that's given because we're going to start with two parallel lines cut by a transversal. So here's two lines cut by a transversal. We're just going to assume L and M are parallel. Okay, how does that help us? Well, there's a couple ways that helps us. We know that alternate interior angles are congruent, which is why I set this up this way, because I know those are congruent. So if these are parallel, I know that angle 2 is congruent to angle 3 because they're alternate interior angles. So that's the alt-int angles theorem. Okay, let's talk about 1 and 2 for a second. Okay, 1 and 2 are vertical angles. So again, by the vertical angles theorem, angle 1 has to be congruent to angle 2. So vert angles theorem. Okay, let's put an angle symbol in there. So if angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, then by the transitive property, angle 1 must be congruent to angle 3. Right? If this is congruent to this, and this is congruent to this, then this must be congruent to this too. That's the transitive property of congruence. Okay? Now there's a transitive property of equality, but we're talking about congruent statements here. Right? We're not using any of the equality equation stuff. So we need to use transitive property. Some people want to use substitution here, but there's no substitution property for congruence, so we need to use transitive property. So anyway, we proved what we set out to prove. So, there's that Latin phrase QED that means we proved what we set out to prove. So we're pretty much done with this. Now on your homework, you're going to use basically 4 important ideas. You're going to use this consecutive interior angles idea. Consecutive interior angles are supplementary. That alternate interior angles are congruent. That alternate exterior angles are congruent. And that corresponding angles are congruent. So these 4 ideas here are the basis for the problems you're going to do on your homework. Okay, so that's what we talked about today in class. If you need help in the homework, you can check out the next video in the next post in the next day for this week, where I'll kind of introduce that homework and help you get started. Thanks for watching.